Hi, in this video we will introduce a class of square matrices called orthogonal matrices, and we will see the relation between orthogonal matrices and orthonormal bases. Okay, let us first recall that an orthonormal set of vectors, well, let me call q1 up to qn, qk, means that we have this relation among the vectors of that set, that when you find a dot product of two vectors from the set, you get either 0 or 1. When the index is different, so basically you have picked two distinct vectors, the dot product is going to be 0. If you find dot product of a vector from the set to itself, you get 1. So the first step is that we want to write these conditions as a very simple matrix multiplication equality. To be able to do that, what we do is that first we note that if I take a column vector and find dot product of that with another column vector, we can get the same number as we consider that Qi as a matrix, n by 1 matrix. So I write without arrow, and then transpose it, so it will be 1 by n. Then multiply it to the matrix Qj. This will be a 1 by 1 matrix. So 1 by 1 matrix is a number. These two numbers are the same thing. So this is very key point in all these computations that you're going to see. Okay. Well, now let Q be the matrix which has Q1, Q2 up to Qk as its columns. And let's compute Q transpose Q. Well, Q transpose is that we turn the columns to rows. So what will happen that column 1, the transpose of that will be row 1. Column 2 transpose would be row 2, and column K transpose would be row K. And this will go up to Qk. When you do matrix multiplication, what happens here is that, well, first row times first column, second column, and so on. So we have Q1 transpose Q1, Q1 transpose Q2, and this will go up to Q1 transpose Qk. That's the first row. Then second row will be Q2 transpose Q1, Q2 transpose Q2, and it will go up to Q2 transpose Qk. And, well, continue this, Qk transpose Q1, Qk transpose Q2, up to Qk transpose Qk. You see that these guys are exactly the right-hand side. Well, if we write that in terms of the dot product of the vectors, well, we'll see that this is Q1 dot Q1, Q1 dot Q2, and this will go up to Q1 dot Qk as vectors, and then Q2 dot Q1, Q2 dot Q2, and we'll go to up to Q 2.q k, and the last row is qk.q1, qk.q2, and goes up to qk.qk. And if you look at these dot products, the entries of this matrix, you notice that this basically finds all the possible dot products of any two vectors chosen from the set of the columns. And well, if the q1, q2 up to qn are orthogonal, then you can see that the first one entry is going to be 1, then 0 up to 0. Then the 2 1 entry is going to be 0 1 0 up to 0, and the last one would be 0 0 up to 1. What will happen is that basically Q transpose Q is going to be equal to identity matrix. And this is exactly what I wanted to mention here, theorem. Q1 and up to QK is an orthonormal set. Well, it means that these conditions, this is equivalent, so if and only if Q transpose Q is identity matrix. So Q transpose times Q is identity. Well, this means that instead of writing those conditions that we had Qi dot Qj equals to 0 if I not equal to j and 1 if I is equal to j, instead of that we can just write this matrix multiplication and that's it. So matrices that have that kind of property is what we are interested in. So these matrices, so this is definition. A matrix, an n by n matrix. So we are just restricting ourselves to square matrices. Matrix Q is called an orthogonal matrix if, well, if you either write it as Q transpose Q is identity, or you can say that the columns of equivalently columns of Q form an orthonormal basis. Well, this condition is easier to check because matrix multiplication is just straightforward, and this is an important notion. So we turn it into different thing, and that set of such matrices are called orthogonal matrices. Let's do some examples before we finish this video. Show that the given examples are orthogonal matrices. Okay, so what should we do? We have to show that A transpose A is equal to identity. So A transpose, this is A transpose, multiplied to A itself. Let's see what we get here. So first row, first column. Root 3 over 2 times root 3 over 2 is 3 over 4. minus or plus negative 1 over 2 times negative 1 over 2 is 1 over 4. Here we have root 3 over 4 minus root 3 over 4. And this one gives us again root 3 over 4 minus root 3 over 4. And this guy here is 1 over 2 times 1 over 2 is 1 over 4 plus root 3 over 2 squared, which is 3 over 4. And as you can see, this guy is indeed 1, 0, 0, 1, which is identity matrix. So that's how we show that this matrix is an orthogonal matrix. How about this one, B transpose B? Well, the transpose is 0, 0, 1, 1, 0, 0, and 0, 1, 0 times B itself, 0, 0, 1, and 1, 0, 0, and 0, 1, 0. Well, this is easy to check because you just multiply, you get 0 plus 1 plus 0, then we get 0 plus 0 plus 0, and you just continue that, and you will see that what will appear is again the identity matrix, 3 by 3 identity matrix. So that is why this matrix B is also an orthogonal matrix. So we will study orthogonal matrices in more details in the coming videos.